Okay. Okay, so good morning and good afternoon. So it's a great pleasure for us to have as the next lecturer, Dr. Michaela Kraus. Dr. Michaela Kraus obtained her PhD in astrophysics at the Max Planck Institute for Astronomy in Bonn, where later she also did a postdoc for 1 year. She was also postdoc at the Astronomical Institute at Utrecht University in Holland and at the Astronomical Institute in Andriov, Czech Republic. She was a senior researcher at the Tartu Observatory in Estonia, and since 2018, she's a senior researcher at the Astronomical Institute of Andriov in Czech Republic. She's an expert with several published papers on evolution of massive stars, focus on pulsations, mass laws, and outbursts, as well as on circumstellar environments like disks, shells, nebula, and about the dynamics and the chemistry of the ejecta. She's the head of the working group Physics of Hot Stars and PI of the POEMS project, which is the subject of her lecture at the CCE. So thank you very much again for accepting our invitation, and please, Michaela, take the word.
Thank you very much, Marcelo, for the kind invitation to present today the POEMS project. I need to share. Can you see my presentation in full screen?
Yes, yes.
Perfect. Yeah, it's my pleasure to be invited to give this seminar about physics of extreme massive stars with the acronym POEMS. And please note that I have written extreme and not extremely massive stars, because we are not working on the very most massive stars, but on massive stars in general, but in such evolutionary phases that we call extreme because the stars undergo eruptions or have other kind of peculiarities that I'm going to introduce in a moment. A little bit of background about massive stars. This is a very idealized life cycle of massive stars, as you may all know from textbooks. The massive stars are usually, or like every star, they are born from a protostellar cloud. This cloud is collapsing and forming stars and maybe planets as well. And then 90% of its lifetime, the star spends on the main sequence as a blue object, compact blue object. And as soon as the star evolves off the main sequence, it increases in size, it turns into a supergiant. Then it cools and becomes a red supergiant. It eventually passes through the luminous blue variable state, becomes a Wolf-Rayet star, and then ends its life in a spectacular supernova explosion that leaves behind either a neutron star or a black hole, depending on the mass of the remnant of the star. And the material that is ejected during that supernova explosion provides the new seeds for the next generation of star and planet formation. Now, this is a very simplistic scenario because we know nowadays that it has many difficulties. One of the big difficulties is when we want to calculate the evolution of massive stars. And I show you here 2 examples that have been compiled by Martins and Palacios in 2013, where in the upper panel we have the evolutionary track of a 20 solar mass non-rotating star at solar metallicity. And in the lower panel we have a 40 solar mass star. And the comparison that is shown here in the different colors are the different evolutionary codes that are in use in the astronomical community. And now you see that for the main sequence, at least at the beginning of the main sequence, they all sort of agree, but that's it. For the rest of the evolution, all these stellar evolutionary models predict completely different paths of the star. And this is something very crucial, because if we cannot trust the evolutionary models, then how can we explain the evolution of massive stars? And the more massive the initial mass is, the initial star is, the worse is the scenario. And you see the big deviations in these evolutionary tracks. Some of them evolve into a blue loop, others don't. And here, for the more massive stars, there is even a bigger mess. But why are we left with such a mess in the evolution of the stars? There are several hindrances for the comprehension of the evolution. And first of all, there is the divergence between the theoretical evolutionary phase. This is sort of what is shown here in these tracks. This is according to the burning stages through which a star goes in its evolution, and the observational phases. Because we observe the star, we only know how it looks like from outside. We see the atmosphere of the star. We can see maybe whether the star has some variabilities. We see the environment of the star, but we cannot look into the very deep interior of the star to say, this object is in exactly this burning stage of its evolution. We don't have such possibilities. The other problem that we have is that we observe many, many different varieties of massive stars that are all evolved. But at the moment, we do not have a solid way to predict whether a star will evolve through one of these, through all of them, or just to selected ones, or whether everything just depends on the initial conditions of the star, like the mass, rotational velocity, chemical composition, etc. And a very crucial parameter of which we are still not very sure, especially not for massive stars, is the information about the amount of mass a star loses throughout its entire lifetime. We are sort of sure about how this looks like along the main sequence, but as soon as the star evolves off the main sequence, we have no solid prediction of the mass loss of a star. But this is something very, very important, because the amount of mass the star loses then determines the fate of the star. Now, when we look at real objects in the Hertzsprung-Russell diagram, then we see that there are many stages of what we call the extreme transition phases. These are stars that shed huge amounts of material, typically via some episodic mass loss or mass eruptions. And I would like to take a few minutes just to go through some of these objects, because most of them are the subject of poems. And let me start with the blue supergiant. The blue supergiants are marked in this diagram here with the light blue stars. And you see they populate the Postman sequence tracks in the B spectral type. Well, we know for these objects that, or we're supposed to know about these objects, that they are well-behaved Postman sequence stars. But it turned out in the last few years that this is not at all the case. First of all, it has been found that in the interior of these stars, some convective shells can form depending on what are the conditions during the stellar evolution, during the main sequence. And that means that the star is able to pulsate. That is something that has not been expected at all during the past, say, 100 years. Nobody expected that blue supergiants are able to pulsate. And another issue is that when you look at these symbols compared to the underlying evolutionary tracks, you see that the models predict that the evolution of the star can pass several times through this B supergiant region in the Hertzsprung-Russell diagram. And that means that we should be able to detect B supergiants that are in very different evolutionary phases. Some can be just beyond the main sequence, others can be, say, maybe after the red supergiant stage. And in fact, it has been found from analysis of their pulsation properties that we can have different populations, and we can distinguish them according to the population, the pulsation characteristics that we see for these stars. When they are just beyond the main sequence, the stars pulsate, but they have only a few modes that can be excited. But as soon as the stars have passed through a red supergiant phase, they can pulsate in many, many modes, including radial modes that have been identified as strange modes. And these strange modes are very important because it seems that these can be linked to phases of mass ejections. And I will get back to that point a little later. So they are not so well behaved. The next type of stars I would like to introduce are the so-called B-E supergiants. Now this is on the right side an artist view of how these objects look like. In the center, we have again a B supergiant, but these supergiants are surrounded by circumstellar disks full of dust. And I have been working with my colleagues, including Marcelo, for many years on these B supergiants and their environments. And now we know that these stars do not just have a circumstellar dusty disk, but they have a lot more. They have molecules, they have the material that is not confined to what one would expect to a smooth disk, but it's more like individual rings, and we do not know how these rings have formed, why they are there. Maybe there are some minor bodies that could form from the material that has been rejected, and it must have been ejected from the star because we could do some abundance analysis that tell us that the material in the circumstellar environment of these objects must have been released from the star itself. But how the star did that, we have so far no idea. Then we have the class of luminous blue variables, and here's just one example of the star H.E. Carinae. I guess you all know the beautiful pictures of Eta Carinae, the most famous one. These stars are shown in the diagram as the black triangles, and as you can see, there are always two positions of these black triangles and a dashed line connecting them. So this means that the stars in their, say, in their quiescent state, they also populate the same domain in the HR diagram as the B supergiant and the B bracket E supergiant. But due to some yet unknown physical effect, they can undergo some excursions to the cool red part of the HR diagram, which is usually called as the Esta cycle. So the star suddenly starts to inflate, become very big. Mass loss also increases during that stage. And then the star sits on the red cool side of the HR diagram and eventually, after years or decades, gets back to its initial state. Also here, we do not really know what is the cause of these cycles. And some of these objects also can show indication for giant eruptions, for which Eta Carinae is the most well-known example. Also, again, we do not know what really triggers these eruptions from LBVs. Then when we go to the red end of the HR diagram, this is populated with the red supergiants. I just mentioned them here for completeness. In poems, we do not deal with red supergiants, but they are also important stars because during this stage, the star is very highly inflated and it has such low surface gravities that very, very tiny disturbance can lead to mass ejections. And these stars usually eject a lot of material before they start their journey back to the blue side of the HR diagram. For the lower mass stars, below about 30 solar masses, the red supergiant stage is even the end phase of the star, and the stars will explode. But those that do not explode as red supergiants, they eventually evolve backward to the blue hot side of the HR diagram. And when they do that, they first encounter the yellow hypergiant stage. And here is a nice example of the yellow hypergiant star IRAS and its phone number that has been observed in the infrared. And you see here on this nice image that the star is surrounded by several dust shells. So also in the yellow hypergiant stage, stars expel material in form of shells or rings or bipolar structures. And we do not really know what is the physical mechanism behind. And this mass ejection also is usually connected with a motion of the star in the HR diagram from the hotter state down to the cooler state. And finally, the stars eventually return to the very hot stage, and then they appear as Wolf-Rayet stars, which also expel their complete outer shells and can form these fantastic nebulae, like in the example here for WR124, before then the star finally explodes as a supernova. So the ultimate goal of our research is to take a deeper look into the mass loss of these objects in order to quantify the amount of mass that is lost during these extreme evolutionary stages, and also trying to find what is the physical mechanism that could play a major role for these eruptions and mass ejection phases. As I said in the beginning, knowing the entire amount of mass that a star is losing in each phase of the evolution then triggers its future evolution. So it is very important. So in order to perform our studies, we decided that we will apply for a Marie Curie or Marie Skłodowska-Curie project of the form RISE. We have applied in 2018, and RISE is the acronym for Research and Innovation Staff Exchange. And that says already that this whole project is based on people traveling between individual institutes. This program promotes international and intersector collaboration. And intersector means that, for example, research institutes and universities are the academic sector, and industry and non-research institutes are called the non-academic sector. So we can travel either between academic and non-academic, or we can travel between academic sectors, but then on an international basis, which for us was very important because since I am in Europe, or many of my colleagues are in Europe, and many of my other colleagues are in South America, such a program was the most interesting for us to perform our research. Now, the funding scheme of this project is such that people need to travel, and they need to travel for a minimum of 1 month to one other institute, and to a maximum of 12 months. And as I said, these are exchanges between European and non-European countries. And eligible people that can participate are researchers starting from the PhD level up to professor or senior researchers, as long as people are employed at the sending institution. Then this program provides money that covers all the expenses for these secondments. But on top, we also receive money that we can use to carry out research, meaning that we can organize workshops, conferences, we can travel to other places, we can visit conferences, we can buy books or publish. So we have extra money that comes with this project and that we can use for our other activities. But we receive that extra money only when people travel. So it is very important that people are traveling in order for us to gain the money that we need for our activities. And the idea of the European Commission for this RISE project is that it should foster a culture of knowledge transfer between the individual countries and to help to turn creative ideas into innovative solutions or products or services. Of course, for the European Commission, it would be more important that we would receive the Nobel Prize, but this is not always guaranteed. They are also happy if we just have a lot of very nice, interesting publications, or if some of the outcome can be used later on by industry. Here I just summarize some project facts. The acronym POEMS I have explained already. It means physics of extreme massive stars. And it is under the Marie Skłodowska-Curie Research and Innovation Staff Exchange Program with the call that was opened in 2018. The duration of the project, it started in 1st of January 2019, and it was supposed to run for 4 years. But due to COVID, we had a suspension period from 1st of December 2020 until April 2022. And we have an agreement that we can extend our project until end of August 2024. The total budget, according to the amount of secondment months that we claimed that we would undertake, is 952,200 euros. And of this, 920,000 euros is sponsored from the European Commission. Now you may ask, and what is the difference? And the difference is, I must say, the amount that actually Brazil should add to the project, because Brazil is considered by the European Commission as an extremely rich country and they should pay for their travel themselves. In reality, we all know that this is not the case, at least not in scientific research, and we are trying to deal with that to cover and back up our Brazilian colleagues so that they are not in need of paying for their travels. And the coordinator of this program is my institute, and I'm the PI of the project. For our project, we need some certain background expertise. So we have collected a multidisciplinary team that consists of many theoreticians, but also of observers. And the team members, they should come from different disciplines that include mathematics, statistics, atomic and molecular physics, astrophysics, astrochemistry, solid state physics, fluid dynamics, and numerical methods. And of course, it is important that we need a gender balance, and we also need to have a balance between early career researchers and more experienced researchers. But that comes as a very natural asset, because usually when you are planning such a project and you see that you have to travel for several months, then most of the older people say, oh, I cannot do that because I have teaching obligations, or I have this and I have that. So it's very natural that the younger people in the team are the ones that are more free to go for secondments. So that's why it's a very natural outcome that each project has a lot of early career researchers. So this is an overview of the consortium of our project. So we have 5 institutes here marked in light blue or greenish that are called the beneficiaries, because these are the European institutes from European countries, and beneficiary because the European Commission thinks that they receive the money and they should then deal with the money. And we have the non-European partner institutes, and we have from the partner institutes Universidad Nacional de La Plata from Argentina. We have Observatorio Nacional in Brazil. We have from Azerbaijan, Shamaki Observatory, and then we have 3 institutes from Chile. Actually, at the moment, we have only 2 institutes left from Chile because Pontificia Universidad left the project, but not the knowledge left the project. The knowledge transferred to Universidad de Valparaíso. So we quitted our contract with the Pontificia Universidad but keep the same people because they were just changing job now to Universidad de Valparaiso. And in Europe, we have Germany included with University of Göttingen. We have Estonia with Tartu University, the Royal Observatory of Belgium, and we have University of Leeds in the UK. And of course, Czech Republic, my institute. And when you look at the expertise that is listed for each of the individual participating institutes, you will see a lot of overlap. So we have stellar pulsations from the observational and from theoretical point of view, stellar winds and atmospheres from both theory and observations, many kinds of stars also from both. And we have also astrostatistics, and we have hydrodynamics, radiative transfer, a lot of numerical modeling. So everything is there, what we need for our project. And we also made sure that we have a good gender balance. And this is an overview of the current composition of the team, split into male and female, and split into the beneficiaries, so the EU partners and the EU institutes and the non-EU institutes. And you see that in total we have pretty good balance between male and female. The only thing that we notice is we have more male seniors, whereas we have more female younger researchers. But the total numbers there, they balance. We have in total 16 students involved, so PhD students, which is very nice because these are the driver of the science usually. Now, the specific objectives that we have in our project, we have formulated 6 different objectives. The first one is that we want to deepen our knowledge of stellar winds. We want to derive comprehensive mass loss rates for the non-eruptive phases, like the classical main sequence stars, and just post-main sequence objects in which they do not yet undergo eruptions. And we also want to find ways how objects can form circumstellar disks from the material that is streaming off from the stellar surface. We want to gain insight into the pulsation properties. As I had mentioned, B supergiants are found to pulsate, but in principle, I think nowadays every star, or almost every star, can show pulsation. So it's very important to study the properties of the various types of stars of this pulsation, and especially to figure out whether these pulsations have the potential to trigger mass loss and mass eruptions, and then to quantify how much mass loss can be triggered by these pulsations. We also want to achieve comprehension of the chemistry. As I had mentioned, these stars all are surrounded by ejecta. We want to figure out how the chemistry evolves, how the molecules are forming, what kind of molecules are forming, how is the dust forming in these environments, and how will this ejected material eventually then interact with the interstellar matter to create structures such as bow shocks and astrospheres. And this is a very interesting point, because but it has been found that many of the evolved massive stars do show bow shock structures in the infrared, and our own observations are more focused now on what is the optical counterpart. Do we see the ionized gas from the stellar winds? Can we quantify the mass loss by calculating backward from the shocked region? And can we get information about what is the dynamics and the composition of these shocks? We also want to unveil the role of binarity for the occurrence of massive stars. We all know that massive stars are mostly born in binary or multiple systems, of which they can lose some of the companions. Some of them are merging, some of them are born in very wide binaries, so the binarity will not influence their evolution, but in many cases it will influence. So it is important to know the fraction of each in these extreme phases. And finally, we want also to improve our comprehension of stellar evolution of massive stars and try to connect the different phases that I have been talking about in an evolutionary scenario. Can we really make connections? What comes first in the evolution? So these are more or less the objectives that we have, and we have grouped our work into 5 work packages. Only the first 3 really deal with science, is the development of analytical and numerical methods for all the different fields that I have been mentioning. But of course, we also need to collect a lot of astronomical data in order to confront our theory with the observations. But another very important work package is related to summer schools, workshops, and outreach. And another one to management that I will not go into detail. It is just very time consuming and mostly related to myself. So I would like to briefly talk about the schools or the activities that we do in the frame of poems, because it is very important. The European Commission is very much interested to see that we disseminate our results, that we communicate our results to the scientific community, but also then to the general public. So we have organized already one summer school that took place in November 2019 in La Plata in Argentina, and it was devoted to pulsations along stellar evolution. So I show here on the left is the poster of that conference and the conference photo with most of the participants. And from that conference, we had also prepared the lecture notes from all the lecturers that have been invited and provided very enlightening lectures about the theory and stellar evolution and pulsations, observational and analysis techniques, and also about diverse pulsating objects. These lecture notes can be downloaded. They are freely available. You can find them in ADS or also on the POEMS webpage. And we hope that they will be helpful, especially for students, to get connected with this field. A second summer school that we are planning right now is about stellar winds and outflows. And we foresee a possible period for that summer school to take place the first 2 weeks in September next year, and it will take place in the Czech Republic. We have just started with the organization, so you have to be patient. I hope that very soon we will be able to provide more detailed information on the POEMS webpage, but also some announcement on the webpage of the International Astronomy Meetings. Or you can also ask your national contact person, which is for Brazil is Marcelo. Then we are organizing POEMS dedicated workshops. This means that these workshops are basically or mostly for POEMS members. And so far we have had 2 of them. The first one was an online workshop that was just during 1 day in December 2021. And it was organized by the Institute of Astrophysics at the University of Göttingen. And we just gathered and we were exchanging, we were reporting about our newest results and had many discussions about how to continue our research within POEMS. And the second workshop we had recently, it was an in-person workshop here in the Czech Republic, because we had many people from the POEMS project as visitors. So it was a rather spontaneous decision to go and have a small workshop to exchange our ideas and to help, especially the students. We had several students here to share knowledge with them about specific items. But we are planning a big international workshop or sort of conference with most likely have the title Extreme Massive Stars, but we will settle that later. It is planned for June 2024, and this one will take place in Brazil. Marcela will be one of the main organizers and Observatorio Nacional for this conference, and it will be open for everybody to participate. And it will be the main platform where we plan to present our final results of the project. We have some budget reserved for this from the Poems project. We will have 30,000 euros available to support the organization, but also to support students so that they can come and participate at this workshop. Then also important, as I said, is outreach. And we had prepared some flyer summarizing the idea of poems, the consortium of poems, some facts, some the science case behind that. And we have prepared that in all the national languages, and Marcelo should have the one for Brazil. And he will certainly be happy to share that with anyone who is interested. Here I'm just showing the English version. For each we provide the national contact. And it is used for outreach. When we have Day of Open Doors, for example, we distribute, we explain to the public what is the idea of our project. Besides flyers, we also have posters where we present newest results, but the flyer is still the most important thing that we use for our outreach. Then we also organize public lectures. And these are things that are done by the individual participating institutes themselves. So this was a public lecture called Stellar Concert. It was given by Julieta Sanchez at the Planetarium in La Plata. It was in the frame of our summer school that we organized. And these kind of organizations happen on the national level. And also we try to be visible, for example, in calendars like the one that has been prepared for Observatorio Nacional in 2020, where poems also was mentioned. We give interviews at radio and TV stations wherever is possible, and we have press releases about the outcome of our results. Now, with respect to the science itself, we need a lot of data, as I have mentioned before, and the data acquisition is done using, first of all, a collection of telescopes that are at our disposal. So, for example, in Azerbaijan, in Tartu, in Estonia, in the Czech Republic, in Argentina, and in Brazil, we have national facilities which we can use, to which we can apply on the national level. And we also have the possibility to apply for ESO telescope time and also to Gemini telescope time. This is done via international South American collaboration. And besides to this data, we also use data from space missions, in particular from TESS and Gaia missions. And we also collect the light curves for many of our stars from ground-based surveys, such as the ASAS or the ZTF or AFSO, or there are many more that we can explore to collect as much as possible of data for the stars that we are investigating. Then data availability is another very important issue with respect to our RISE project. And we are preparing a database which will be freely available to the community at the end of the poem's lifetime. And in this database, we will provide all our observational data that are required. And we will also provide all the computed models that we will generate during the frame of poems. These are grids of stellar wind models, grids of molecular models, grids of stellar parameters that we derive, etc. And everything will be made available to the community. We have already one first grid that is available under this web page. It's called Isósceles, and it has been prepared by University of Valparaiso in Chile. The content of this grid is basically spectroscopic line profiles calculated from a combination of hydrodynamics, computed with the code Heidwind. That is something that had been developed by Michaela and his team in University of Valparaiso, combining the output of this Heidwind code with the non-LTE radiative transport, which is computed with the code FastWind. And the name of the grid is isosceles, which means grid of stellar atmosphere and hydrodynamic models for massive stars. And I just show you how it looks like when you go to the web page. You start with the first screen that you see is this one to the left. You have here a grid. You click somewhere that will provide you a parameter space. Then opens this table to the right, from where you can select the specific model that you would like to inspect in more detail with these parameters: mass loss rate, terminal velocity, temperature, log G, etc. And then you have the option to click or select the spectral line that you are interested in. You can select all of them, or you can just select some of them. They are from hydrogen, helium, and silicon. And then you will receive, now for this example, I just clicked on H alpha, and you will receive for this specific computed model the H alpha profile in a normalized way for here the different turbulent velocities. And you can download and you can compare with your observed spectrum and see whether this fits or not. And I think I have just time for a few science highlight results from our project. Of course, we have been working for 2 years already, and there are many publications that are on our webpage. I don't have time to go into all the details, but I just would like to show you some very nice results. For instance, we have gained new insights into the structure of stellar winds and mass loss. And there's this very nice paper by Alex Gormaz-Matamala about evolution of massive stars with new hydrodynamic wind models. And when you look at that paper, you will find the figure 7, which shows the evolution of the mass loss rate along the evolutionary tracks for different initial masses, calculated in his new self-consistent way. These are the solid lines, and in comparison with the classical tracks. And you see the big differences in the mass loss rate that he obtained. And this is very significant because, as I said, mass loss rate determines the fate of the massive star. When you look at the evolution in the classical HR diagram, so with the temperature and luminosity, then you will see that only for the higher metallicity, like the galactic one, there is, I would say, significant deviation in the evolutionary track with these self-consistent models that have been calculated in our team. So that is something very interesting. And a second thing I would like to highlight is that we have achieved a better understanding of instabilities that are at work in massive supergiants. And this diagram shows some example. It has been calculated for parameter space of yellow hypergiants, specifically for the yellow hypergiant Rukas, for which we know that it had several outbursts in the past. And we have performed a stability analysis with respect to linear non-adiabatic radial perturbations. And you can see in this modal diagram, here is the frequency of the excited pulsations. And on the right side, you have the imaginary part of the frequency, where you get information about whether, when they are negative, whether this mode is excited or not. And we have here the interesting case that many modes are regular, they are sort of in parallel, but then you have modes that are crossing each other. And this crossing is, these are the modes that are highly unstable and with very high growth rates. And this means that these modes are really suitable to eject mass from the stellar surface. And we are trying to quantify the amount of mass, but so far we are not very successful, because with every mass ejection, it also ejects the grid from your numerical model. So at the moment, we haven't been able to fix that. But it's an interesting result, because it may help us to understand why these objects like this, the Fried Egg Nebula, can eject huge amounts of mass. And for that star, it has been found that it had at least had 3 mass ejections. It is surrounded by 3 shells of dust that must have been ejected within the past 100 years. Another very interesting result, again for a yellow hypergiant, is that we have detected for the first time water vapor. There have been some other low mass stars around which water vapor emission has been found, but for massive stars, this is the first discovery. And just to show you how that looks like, the top panel is the K-band, or a portion of a K-band spectrum, the near-infrared region, where we detected CO band emission by this very characteristic shape. And we knew already that this star has CO band emission, and we were interested in the kinematics, and that's why we got this very high resolution spectrum taken with IGRINS at Gemini South, and to resolve the head structure in order to get the kinematics. And then we were modeling the CO, which is shown in the second panel, and we thought there's so much noise that looks like some emission, but we could not at first identify what it is until we found that it is from water vapor. And then when we calculated a theoretical spectrum of water vapor, which is shown in the third panel, and then we combined the 2 models, then we were able to reproduce the observations. And this is a challenge, because it requires some new approaches to the interpretation of these stars. We have also spotted the presence of a transitory ring around a classical BE star, which is the star 12 Wool, which we observed during its active phase, and later on, from every now and then, we take spectra in the infrared. And one of these spectra, which is this one with the blue dots, blue marks here, showed CO band emission, which is not usual at all for BE stars. Usually BE stars, when they start to expel matter, then it's basically ionized gas, just hydrogen emission. But this is the first object showing molecular emission. And it might be a hint that there could be a connection between the classical BE stars and the B bracket E stars, for which molecular emission is very normal. As I mentioned previously, we are also interested in the fraction of binaries in the different types of evolved massive stars. And this here is one class of stars, the LBVs, that have recently been investigated, and for which a binary fraction of about 70% has been found, which is very interesting, which poses new constraints to binary evolution in massive stars. And this detection has been made from a combination of multi-epoch spectroscopy and long baseline interferometry that was used to probe the separations from 0.1 to 120 milliarcsecond around a sample of LBV and LBV candidates. And finally, we have also obtained very precise stellar parameters and hence classifications for a sample of B bracket E stars, and that is a work that has been led by researchers in Brazil from Observatório Nacional. And this analysis made use of high-resolution spectroscopic data from ferrous and photometric data. And it shows that it's very important to have very high-quality data available in order to classify stars in a proper way. All our publications are available on the POEMS webpage, which you can find here. And just to come to an end, our next steps is, of course, that we want to complete with the theoretical investigations on the different subjects, which are the stellar winds and how they transform into outflowing disks. Then the astrosphere descriptions, which is very important because we have already a huge amount of data available with which we can then compare our theoretical models. Also the chemistry, which is all work in progress, and the pulsation instabilities, which is also a work in progress. And we also, of course, wish to complement our available data sets, for instance, with the IView and long slit spectra across the nebula and the ejecta that we have detected for many objects, and also for the astrospheres in order to derive physical parameters, and also to continue collecting light curves for performing pulsation analysis in order to test the pulsation theories, and to continue with speckle interferometric observations as one specific tool to reveal faint companions. And of course, we want to complete the analysis of the data with the newly developed codes in order to achieve our ultimate goals and to make finally everything available to the community. And with that, I would like to stop and thank you for your attention.
Thank you very much, Michaela. It was a very nice talk. So are you open for questions? Any question? Okay, Simone, please.
So thank you, Michaela, for this very complete overview on poems. And I'd like to ask the spectroscopic data that you have for these extreme mass stars are usually based on emission lines, right? You don't have access to photospheric lines, to absorption lines, right?
Yeah, for many stars, yes.
Okay, so this chemical analysis you plan for environmental evolved massive stars is related to the ejecta, right? Or
yes.
to the winds, not to the
yes.
photosphere. Okay.
Yes.
Okay. Thanks.
Thank you, Simone. Renato, please.
Okay. Hi, Michaela. Very interesting talk. I had actually a couple of questions. One thing that I noticed is that the data that you mentioned there seems to be, well, in a way, heterogeneous because you have different instruments, different telescopes, and so on. On the other hand, it seems like it's preferential optical. I mean, there's no, for example, X-rays data or something like this. And I was wondering if that is on purpose. Is they irrelevant for this to solve the issues that you're trying to solve with the stars or not? And if there is any facility which is dedicated to collect data for poems.
Well, with respect to X-rays, no, we do not have X-ray data for our objects. They can become relevant for some stars, or, for example, for shock regions for the ejecta. But we also don't have an expert working on X-rays in our team, I must admit. And telescopes dedicated to poems, well, we try to use as much as possible the national facilities. Well, here in the Czech Republic, we have a 2-meter telescope that is right in front of my office. I can use, not every night, of course, because we have several working groups here. We need to share the observing time, but still a significant amount of time is dedicated to poems, yes. The same is true for the Tartu Observatory. They have the telescope even for them, just for poems, with the disadvantage that the weather in Estonia is usually much worse than in the Czech Republic. So they do collect a lot of data. Then we have regular observing time with Casleo, for example. Our Argentinian colleagues regularly submit proposals and get a significant amount of observing time. And for the others, you know, ESO or Gemini, it is just we need to have luck in order to get proposals accepted. But I must say that especially for Gemini, we have a lot of luck using Argentinian time, and lately also combined with Chilean and Brazilian time sometimes, because we have just experts in infrared astronomy that are excellent in writing proposals, and our projects usually receive time or are accepted, and whether the weather will allow that we will get all the data is another question, but usually we have a very high success rate in collecting data. So we really sit on a huge amount of data already, I must say. And for other parts, like we were mapping in H-alpha, for example, we made a survey in H-alpha imaging. For that, we used our telescope and also time that we bought at the Danish telescope on La Silla, for example, or with other telescopes that they have robotic facilities like the Eye telescope net, which offers to buy, you can buy telescope time for different facilities distributed all over the world, and that we used to collect the data that we needed. So yeah, we have a lot of data that we can work with.
Okay, one very fast question, since I'm not from the field. I saw you didn't mention very much the question of metallicity. I saw on the last plots the Z was there somehow, and I was wondering what's the importance on the metallicity, initial metallicity, for this funny behaviors that sometimes indistinguishable from red, a bright red star, I don't know, from a blue one, and how does it play a role in that?
It does play a role. It is very important to know the metallicity of your stars, because the evolutionary tracks look very different when you use a different metallicity. But when we, for example, we are dealing a lot with Magellanic Cloud objects, or also stars from other galaxies for which we know relatively well the metallicities in the local group, then we can handle that. But we know, of course, that the stellar wind theory depends on metallicity, and how everything will work is still something that we need to figure out. But my colleagues in Chile who are doing the wind modeling, all these theoretical analysis, they are very well aware of this issue. And that's why this paper that I've shown from Alex Gormas Matamala also had already included the metallicity effect, showing that in particular along the main sequence for O-type stars, metallicity plays a crucial role for determining proper mass loss rates.
Mm-hmm. Okay, thank you.
Thank you. So, any other question?
Yes, just let me take this advantage of this of Renato's question. And so the metallicity is derived usually from photometric calibrations or from emission lines. How do you derive the metallicity?
You mean now the metallicity or the abundances?
Metallicity.
Metallicity. Well, for Magellanic Cloud stars, well, you use the average metallicity of the Magellanic Clouds.
You use the average.
So for these different galaxies, the sort of metallicity is known. We know that some galaxies have some metallicity gradient, and it's important to know in which part of the galaxy the stars are located, but these are usually constrained.
Okay, so you don't derive the metallicity for each particular object. You
No.
assume the average metallicity for the galaxy. Oh.
Yes, but we derive the abundances for our objects.
Based on emission lines?
Well, if possible, based on absorption lines, but yes,
okay.
this then works only for the classical B supergiants.
Okay, okay,
For the emission line stars, it's not really possible.
okay. Okay.
Okay, so any other question? I think the students are a bit shy.
I know we have students in this field here in the audience.
Yeah, exactly, but they are a bit shy. But Michaela, I would like just to emphasize that the next school and also the final workshop will be open for the whole community, okay? Not only for the poems group. Yes, that's right, no?
Yeah.
So as soon as we have more information about the school and also the final workshop, the information will be provided at the poems website and also at the Observatório Nacional website.
Perfect.
So the people need to be tuned. Okay, so any other question? No? Okay, so Michaela, thank you so much.
Marcel, there's one person.
Yeah.
Oh, sorry, Reinaldo, sorry. Please, Reinaldo.
Hi, Michaela. This is Reinaldo Rosa from INPE. Actually, it's not my field of research, but it's a very nice issue to apply our methods here in numerical simulations. And but I came here just to say, if you can send my regards to Marian Karlik, okay?
Marian Karlitsky.
Yes, okay. It's a long time I never stay with him. He came and stay with us for 2 years at the INPE. So please send my regards if you can.
Okay, thank you. I will do that. Thank you.
Thank you.
Okay, thank you, Reinaldo. So any other question? Comments? No? Okay, so Michaela, thank you so much again for accepting our invitation. It was really nice. Thank you.
Thank you very much,
Thank
Marcelo.
you, Michaela.
See
Thank
you
you.
soon.
See you.
Bye-bye.
See you soon.
Bye-bye.